Okay, I think let's go ahead and get started. So I'm really happy to have Shadi Nogabi here. She's a student at UIUC, a PhD student there, and her research interests span everything you could possibly care about, like distributed systems, cloud computing, edge computing. She's also, I'm particularly excited because she's also done production scale work at both Microsoft and at LinkedIn before they came together. And so today she's going to tell us about some of that work.
Thank you. Thanks for the introduction. So yeah, I'm Shadi Nogabi. I'm a fifth-year PhD student at UIUC. And today I'll be talking about my work around my thesis, which is around building large-scale production systems for latency-sensitive applications. Feel free to stop me wherever you have any questions. So today, with this whole increasing engagement with technology, there are many interactive applications that have emerged. For example, we have social networks where users from all around the world are uploading and viewing photos, and that's like generating hundreds of petabytes of data to be read and written. And when we upload something, we expect our friends from around the world to be able to see it within at most a few seconds. Or if you think about companies that have ads, they're processing trillions of events, and they want this ads to be based on the recent activity of the user, at most like the past few minutes of what they have done. And pushing it to the extreme would be these new applications around smart homes, smart factory, where there are millions and billions of small devices, and in many cases they want the latency to be within a few milliseconds. Something common across all of these is, first of all, low latency is an important requirement. So these applications are sensitive to the latency that they have, and not reaching that latency can mean loss in revenue, or for a factory it could be a whole production line going wrong. And the sensitivity is different. It could be seconds, minutes, milliseconds, but at the end of the day, they're all latency sensitive. The other thing is, as we all know, there's an explosion of data. There's always more and more data being generated, and that means that we need to have large-scale processing. And my focus has been, how can we build these latency-sensitive systems at a production scale? So throughout my work, I've looked at many different areas. I've looked into storage systems. Specifically, I worked on a geo-distributed storage system with LinkedIn, for storing all of their media objects, which was published in SIGMOD 2016. I looked into processing, where I worked with on stream processing systems and how can you handle large amount of durable data along with your processing, published in VLDB 2017. I looked in communication, like container communication, and how can you optimize that. And these are all in the context of the cloud. But as we're seeing, there are many applications that cannot be simply handled by the cloud alone. And what I'm currently looking at, the part that I want to do in the future, is all around the edge. And how can you push computation to the edge, where I'm working with the Azure and Windows IoT teams to look into that. Throughout this talk, I'll be focusing on one of my work and touching on the future work that I want to do. So let's first take a look into Ambry, which is LinkedIn's scalable geo-distributed object store. This work was done in collaboration with the folks at LinkedIn and the DPRG and SRG group at UIUC. Just to pause, can you all hear me well? Okay. So we all know media is everywhere. If you think about social networks, we upload our beloved cat photos, our videos, slides, etc. And if you think of the big picture of all the users, there are hundreds of millions of users from all around the world that they're uploading and viewing hundreds of terabytes to even petabytes of data per day. But something unique about media is that we upload it once, like when we upload our photos to our album. We are accessing them from all around the world, like when our friends are looking at that data, making it both read-heavy, and also the data popularity changes over time, so it's skewed mostly toward the recent data. They're rarely deleted, like nobody deletes anything from their albums, and they're never modified, making them immutable. Our goal in this project was, how can we build a geographically distributed system that can handle these read-heavy, mutable objects with low latency and in a scalable manner? And that's why we built Ambry, where AMRI is actually the mainstream production system for all media objects at LinkedIn. So anything you upload in your profile, in your timeline, or contents on SlideShare. And it has been used across more than 450 million users. It is open source, so you're welcome to go and take a look at the project. But you might ask, what is challenging of building such a system and why is it hard? So first of all, there's a wide diversity across the objects, both in terms of their types, so photos, videos, and in terms of their sizes, where profile pictures can be as small as like tens of kilobytes, and videos are as big as a few gigabytes. Secondly, users always expect everything to be fast, durable, and highly available. So if they upload a photo, they want it to never be lost, everyone able to see it fast, and that means that you have to have geo-replication, and it has to be done with low latency. Third, there is an ever-growing amount of data and requests. As I said, data never gets deleted, so it's always piling up, and we're getting more and more data. But if you even take a look at just the request rate alone, at LinkedIn it was doubling almost every year. And fourth, there are many causes for load imbalance. So throughout the day, different days of the week, we have workload variability. And another big issue is, since data is always growing, you always have to add more machines which have no data on them to a cluster that already has a lot of data on it. And toward that, there has been a solid body of research generally around storage systems. So one big category would be distributed file systems such as NFS, HDFS, etc., which are very good for large objects. So if you want to have a gigabyte large object, they're very good, but they're not well designed for small few kilobyte objects because first they have a high metadata overhead, both the metadata itself and the fact you have to go and fetch it from a different entity. And also, there are some unnecessary features that are not needed, like a hierarchical structure or the access control list in our case. On the other end of the spectrum, there are key value stores such as Dynamo, Cassandra, Bigtable, which are good for small objects, but they're not well designed for gigabyte large objects, and they're typically not designed for a geo-distributed environment. And to fix this, there is a category of more tailored systems, which are like blob stores, such as Haystack, F4, Twitter's blob store. But these either do not resolve the load imbalance issue or are not designed specifically for a geo-distributed environment. Yeah.
So is the geo-distributed requirement, is that a result of your desire for low latency or something?
So there are two main reasons for that. One is low latency, especially for reads. So if I upload my photo, I want my friends from different points of the world to be able to see it, and also for availability. So if there is some reason that the data center is somehow disconnected, I want the data to be available in other data centers.
So
Yep.
just a quick question. So just to clarify, the geo-distributed part is not for someone in Twitter to analyze the data set. It is for user to access the data.
Yeah, so this is not a system for analyzing data sets, so probably something like HDFS would be a better system for that. That can, I'm not saying you cannot use it.
It's just tailored for a small, for a large object.
Yes, but when you're analyzing a data set, you look at a lot of data at the same time. Isn't that true? Yeah. Is there any other questions? So, to go back to how we built AMRI, we looked at the challenges and we built it with four main goals in mind. First, we aimed for low latency for all objects. We want it to be geo-distributed and scalable so that we can keep up with this growing scale, and also working in a load balanced fashion. And toward each of these goals, we have used a number of well-known and our own new mechanisms and techniques. And I want to point out that this was a production system which I was fortunate to join from the very beginning. But as any production system, it was a big team of people that were working on it. And today I will talk mostly about my contribution and the part that I was the part that was led by me. So first, let's take a look into geo-distribution. So let's say we have a user, Alice, which is trying to upload some photo item I, and that needs to be replicated in all these data centers. So for this data to be replicated, the user is going to be closer to one of the data centers and can write it fast there. But the overall end-to-end latency is going to be dominated by the fact that the other data centers are far, and you're going to have a slow cross-data center traffic. And if we simply do a location-agnostic replication, it's not going to work well. So what we do is similar to some other systems, is something we call asynchronous replication, where we only write synchronously to one data center, and we count it successful at this point. So from the point of view of the user, when it's written to one data center, it's already uploaded. And then we use background mechanisms to replicate the data to other data centers. So essentially, we're leveraging locality in a sense that we write data just to the closest place and we don't move it around. And then we use background mechanisms to replicate it to other places. And by doing so, we reduce the user perceived latency, and there are many opportunities to minimize the cross-data center traffic. But there are some challenges in doing the replication, and it's not as simple as it seems. So first thing is, if you want to be able to always look at your local data center or the closest data center to you, you have to have an active-active design, meaning you should be able to read and write from any data center, any replica. So if Alice has written its object in data center 1 and her friend Bob wants to read the same item, while the data has not been replicated yet, it's not going to be able to see it. So what we do to fix this is something we call proxy requests, where we take the request and proxy it to other data centers, trying to find it and fetch it from the data center where it has the data. Although this is expensive, we saw that in practice it doesn't happen that often, so like less than 0.001% of our requests go through this whole proxy requests. The other thing is about the yeah, go ahead.
So the proxy request will actually go to the source origin data center?
Yes, so it will try and different data centers to find it.
How long do you need to do this before? You just do it until you know you've confirmed that things have been replicated, or you just use some heuristic and say, I'm going to do this for 5 seconds or something?
So we do it until we tried all data centers. Any other questions? Yep.
How do you know that item I exists?
Yeah. So something I didn't mention is this is not particularly a key value store. It's a handle store. So what that means is when you write or when you upload a data, it returns back to you a handle that you can use to get the data. And within that handle, there is some information encoded that where that data is placed. So we can think of it like as a URL, and then that URL is used in the website. So Bob can see the URL, but not the data itself.
So I'm a bit confused. So the data, the item I, is propagated to all data centers in the background in a periodic fashion, or it's purely in a passive way, like when someone else asks for the data, you propagate it to other data centers?
No, it's done periodically. I will get to the replication like in 2 slides
I see.
of
So
how we
this
do
is-
the replication, but it's periodic replication.
I see.
So it's in a passive way, or is it active?
Passive way.
Passive way, yes. Any other questions? So, but then, as you mentioned, how do we do the replication? We had like 3 main observations here. First of all, our data is immutable, so we don't need any of those complex replication mechanisms with versioning and synchronization, because we only have one version of the data, and it's either there or it has been deleted. Secondly, we wanted the system to be load balanced, so we don't want like one subset of the nodes to have a lot of overhead. But and on the other hand, we don't want to have a lot of cross-data center synchronization. So we don't want like leader-based designs where we want to have to know the leader so that we can do the synchronization, because then you have to synchronize the leaders across multiple data centers and make sure they are up to date for you to be able to do the replication. So we were looking for a simple, balanced, and master-free design. And what we do is a 2-phase background replication. Let's say I have replica 1 that wants to replicate to replica 2. What happens is in the first phase, it just asks for what are the things that are missing. So it's like a fast match that asks, give me all the IDs after the last time we have synced. And replica 2 is going to send the list of IDs. It's going to filter out which ones it doesn't have, and then the data is going to be sent. And they update the last offset they have synchronized. And this is done in an all-to-all manner, so every replica does this independently with any other replica, and in a periodic manner. Is there any questions? Or yep. Sorry? So deletes are treated as another write, but just a write that says, hey, this is deleted. So it's just a small entry that has a flag set as deleted. And so it's at the beginning, it's a soft delete. So it's simply just add another object. And eventually, we remove them and compact everything. Yes?
Two questions. One, I thought there were no deletes because it was media data that you didn't want to.
They're rarely deleted.
Oh, okay. And then.
But they're not modified, so nothing is updated. There's only one version of it.
And then when you say get missing data, I didn't understand how Replica 2 knows what's missing.
Okay, so there is one detail that I should probably add to make that more clear. It's not actually done that every node talks with every node, because that's crazy. Instead, we group objects together into this unit we call partition. So you can think of this as a grouping. And you have to coordinate with other replicas of that grouping. So let's say I have this big group, and I have group 1, group 2, group 3, group 4, and group 1 has a number of objects, group 2 has a number of objects, and group 1 has a number of replicas. So essentially, group 1 has to coordinate with other replicas of group 1. So it knows who to coordinate with. And then you have a last offset within those two replicas. So like you have this offset that you know until when did they replicate. So they ask, give me whatever you have written after the last time we have synced. Anything else? So the next thing is about load balancing and how do we provide that. So the first, we looked into two cases. The first is a static cluster, meaning that no new nodes are added or deleted from the system. So you have a number of nodes and nothing is changing in terms of them. And how can you make sure the nodes grow in a balanced state? So both in terms of their usage, their disk usage, and also the request rate, so how much requests they're getting on each node. And to fix this, we use three techniques. First of all, we use random placement. So whenever we want to place an object, the decision of which of those groupings to put it on is completely random. And then we have geo-constraints of where to replicate those different groupings. And by that, we expect to have an equal number of objects per node. But this does not mean the nodes will grow equally. So we could have a very big object that can actually starve the system and hog a lot of the resources. So we chunk the large objects into smaller ones, and each smaller chunk is treated independently and replicated randomly. So essentially, by using random placement and chunking, we expect an equal number of bytes per node to be growing, so the usage grows balanced. But this still does not handle how do we have equal number of requests. And for that, what we do is we have a caching layer on top of our system. What this does is you have a distribution of data, and you're essentially putting the very hot outlier data into the cache. And in the nodes themselves, they store typically millions of objects, so the rest of the distribution is almost the same across the nodes as well. And we remove the outliers by serving them in the cache. Do you have any question? Yeah.
So the chunking is used to make things more uniform in terms of size. What chunk size do you use, by the way?
We use, I believe, something between 4 to 8 megabytes.
Between 4 to 8 megabytes. And then, are you saying that the caching layer can basically absorb popularity skew enough to make
the super popular data? Like, for example, if a celebrity posts something that everyone wants to see, that caching layer can absorb it.
So it's good enough for dealing with hotspots?
Yeah, actually, so not like it doesn't make the rest of the distribution uniform because it's going to be a Zipfian distribution at the end of the day. But we're taking the very hot data out of this. I think like if I am correct, like 30% of the requests are actually served by the cache. So like 70% of the actual traffic goes down to the system itself. Yeah.
So is cache here a different storage mechanism?
So this is
it like it's hot and RAM?
this is like
versus disk, or is it something else?
Yeah, so no, this is a CDN, so it's outside of the whole environment, and so it's like completely outside of the whole system, so it's just absorbing all of them. And I believe the CDNs use memory. Within the system itself, we also use caching. So within these nodes, we also leverage the fact that we have memory and disk. So we use the memory for the hot data within that. But some of the data, like as I said, like if a celebrity shares a photo, that's like extremely popular. So it's going to create a big skew. That is served by the CDN layer. Yes?
If you chunk a large object
Mhm.
and spread it out, does that make it slower when you need to read that object?
So actually, it makes it better than writing it sequentially, because now you can read and write in parallel. So you can read and you can write a bunch of the chunks in parallel and also read them in parallel. Obviously, you don't want to read it completely in parallel because it's like using a lot of resources. So we limit how many, essentially the window size, or how many of these chunks you can open and have and read or write at the same time. Yes.
So I don't know if this is. Suppose you're watching a big video,
Mhm.
and you're only watching, most of the time you only watch the first maybe few minutes, or you skip someplace, and you have all these chunks and you have this parallel stuff. Do you know if anything is done to deal with that case, that you don't want to read everything in parallel?
So it's essentially streaming it back to the user in a sense that we don't read random locations of the chunks. So we start from the beginning and we read a few chunks, and then you stream it back.
You do that in parallel.
Yes.
I see.
Any other questions? Okay. But the more interesting scenario is when you have a dynamic cluster, because in reality it's not like nothing changes in the system. And actually, because we have continuous growth, we always have to add more and more nodes to the system, and these nodes have no data on them, while there are some nodes in the data center that already have old data and cold and old data on them. And because of that, we have cases where we see huge imbalance. And to fix that, we have built a rebalancing mechanism that uses two things, but again, the usage and the distribution of hot and cold data, and tries to move everything to a balanced state. Something we found is, so hashing mechanisms don't work well for us. And the reason is when we're adding these new nodes to the system, essentially we are in a case that we don't have a lot of capacity left and we're close to a saturation state in the system. So at that moment, we don't want to start moving a lot of data around just for the system to be able to work again. And to do that, we built our own rebalancing mechanism that finds the ideal state. Like if we were to put all of these objects right now, what would the ideal state be? And starts to move toward that, but it does it in the background. So whenever the system is low, it's not using a lot of the resources, like overnight, it starts moving things around. Yeah. But even in consistent hashing, don't you still have to move things around for, like, it provides the... Yes, that is true, but we didn't want to be tied to the fact that we have to have the data in these specific locations for the system. Because essentially you're affecting the availability of your system. Yeah. Yeah.
This way of the background thing, like figuring out how to get to the ideal from where you are, that sounds like a not easy problem.
So we are using a heuristic.
Okay.
It's not completely moving to ideal. So computing the ideal is not that hard because you know all the data. It's just all the data divided by the number of machines would be how much usage you want, and you know the distribution of data. So you know what the ideal should be. What we're doing is actually moving things in groups, and we categorize the groupings into different categories of this is very hot, this is very cold, this is very like medium or something like that. And then what we do is we start from the ones that have a lot more than what they should have compared to the ideal state to the ones that have much less in the ideal state, and we start moving things between them. I agree it's not an easy thing, it's just a heuristic in a sense, but it did work out well for us. And yep.
So these background are geo-specific, right? Because
What do you mean by that?
So how do you deal with around the clock and news being hot? So a celebrity posts an image in Australia, it gets picked up in Australia during the night here, and then in the morning it's very hot, and this and that.
Sure.
And
So we are isolating this per data center in a sense that we add nodes to one data center at a time, and the rebalancing is done within that data center.
Right.
Did that answer your question? Yeah. Yep.
Just to clarify, these nodes are new machines
Yes.
added to a data center, or
Yes.
new data centers added to the pool?
This is new machines added to the data center. When there is a case that you can add new data centers, but that is actually a very extreme case, and it's not like you add a data center and you start running it immediately.
Yeah, actually, so that's my second question. So how does linking make this decision?
So-
when to add, how many machines to add, and how many data centers to add?
How many data centers to add? I don't know. That's like a very high level business question in terms of they look like there are a lot of business people that take a look at what is the profit of adding this, how much latency would it help, which locations should I add it. So that is something that I really cannot tell you. But in terms of how many nodes, so that is based on the demand. So if you look at your system, you can see that, hey, I'm at almost 70% capacity used throughout my system. And if I continue with the same rate that I'm continuing per day that I'm adding data, I will run out of capacity in the next 3 months. And then you plan ahead and say, now I should add some machines so that in the next 3 months I don't run out of capacity. But on the other hand, you don't want to add a huge batch because machines are becoming better and better. So if you wait, you can get better machines. So there's always a trade-off space. And in terms of the exact numbers of what they add, again, these are mostly done by business teams that look at the merit and everything. Yes?
I have a question about how you determine if a client is closest to a data center.
That is a good question. So that is abstracted out of our system in a sense that there are multiple layers throughout the whole stack. And I know there is a load balancer that at some point catches the request and decides which one is closer, and the users have some stickiness to a data center. But that is generally how I know it's done.
So the client would then, something tells the client that this is the closest data
Mhm.
center, and it would reconnect to that data center.
Yes. So the user's request doesn't actually go directly to the data center. It goes through different layers. And that request goes to a layer that layer decides which is the closest data center from this user that's coming from this IP. And based on that, it directs it to that data center. Even if later on the user sends the same request, it never goes directly to the data center or Ambry itself. Any other questions? So let's take a look at a few experimental results. First is how do we do in terms of latency? So in this graph, we have different object sizes from 0 to almost 5 megabytes. And then on the y-axis, we have latency. That's the end-to-end latency in milliseconds to get that data. And we looked at a couple different workloads. One is minimum, which is just how much would it take to simply read it from the disk. So that is like outside of Ambry, if you want to read that data from the same disk as we had, how much would it take? Then there's sequential, which when we write a number of objects and we start reading them sequentially and we see what is the end-to-end latency. And then there is random, which we write and we read completely random objects, and a mix, which is a 50-50 mix. And here, as you can see, so our sequential is actually very close to the minimum itself, showing that the system, it does not impose a high overhead in getting the data compared to what it takes to read the data from the disk. And in terms of random, it is higher, but it's a constant overhead of roughly like 15 milliseconds, and that's mostly because of the disk seek time, because we're using HDD disks, and that is because of that. And there's also a linear growth with the object sizes. So, and we didn't go beyond 5 megabytes, in this graph, because it chunks the data after that. So I don't have that graph. Yeah.
This doesn't include the sending the data through the network.
This is from the moment it enters our system So not the user's latency sending it from its device to the data center. The other thing is geodistribution. So we're writing only to one data center, so latency doesn't really make sense. But more importantly is about how does our replication work. Where what we do here in this graph, on the y-axis you can see the average bandwidth used for each node for replication. So like for each node, how much bandwidth does it use? And the y-axis shows us the CDF across all nodes. And this is both within a data center and across data center. So across data centers, as you can see, we have a relatively short tail. So our 95th to 5th percentile is 3x. And this is mostly because of our load balance design, where everyone is contributing equally to the replication. Within data center, it does have a longer tail, but a lot of the values are 0, so whatever is omitted is 0. And that is mostly it happens mostly when there is a failure or something goes wrong that the request didn't get to the node, so it's trying to replicate it from other nodes within that data center. And then there is load balancing, where we look at two factors, the request rate and the usage. And we measure two metrics. So one is across all of the nodes, what is the range and what is the standard deviation. And we measure the ratio of improvement using our rebalancing mechanism compared to the baseline. So the baseline is 1x. And as you can see, we get almost 6 to 10x improvement. And the baseline is whatever we had before, which was the manual rebalancing done by the sysops. Yeah.
What is the usage range thing?
So it's like range, which is maximum minus minimum, in terms of usage. So there are two factors. One is the disk usage, like how much of the disk is used, and the other one is the request rates. Like this disk, like this node is getting 100 requests per second, the other one is getting 1,000 requests per second. And across all of the nodes, we measure the range and the standard deviation.
So usage means
capacity, raw disk capacity used.
And the baseline is, remind me again, what is it?
That is like what we had before, which was someone manually fixing it.
Okay.
Because the system didn't have any rebalancing at the beginning. So far I talked about the work I did in Ambry. Is there any other follow-up questions? Or okay. Now I would like to talk about the next part, which is my future work, the part that I'm most excited about. And we see that the cloud is great. It provides a lot of flexibility and features, and it has enabled a lot of applications. But there are a new emerging set of applications that simply the cloud is not a good option for it. One main reason is latency. So in many cases, the latency of going to the cloud is simply too much. Like if you have an online gaming, when you kill someone, you want them to be killed immediately. Or if you have like virtual reality or augmented reality, our eyes see latencies beyond 20 milliseconds and it makes us sick. Or self-driving cars, you definitely don't want to hit someone. So simply because of latency, you cannot afford going to the cloud for many cases. Some cases it's also because of resources. Like if we had cameras all around this building and they were sending data to the cloud, they would generate hundreds of gigabytes per second that is just not affordable to send to the cloud. Or because of heating, battery, and other constraints, you don't want to use the cloud. And another reason is also privacy and security, like if you have a smart home or especially a smart hospital that has patients' information, they don't want to share that data to the cloud, at least unencrypted. And toward that, there is this whole notion of edge computing that has emerged, where instead of just relying on the cloud, you want to move the computation on these edges along with the cloud, where the edge is just a small device. Let's take like 1 or 2 Linux machines that are closer to the end users, and they're spread everywhere, so you can find a lot of them. And I think edge computing is a very interesting idea, and it's something that is going to be the next step. But I feel there is something missing in this whole environment, and this is like what my grand vision is for the thing that is missing, which is you need to have something I call flexible computing. In a sense, you want to be able to compute seamlessly on any device. What I mean by that is, so you have an application developer that has an application in mind, like in form of a DAG or some way of computations, and some requirements in terms of cost and latency. And from that application's developer's point of view, they just want to have resources viewed as a black box. So they know it's somewhere that they can run their application on. But within that resources, there are clouds, different edges, they have different constraints, different capabilities. And this application should be able to run across the whole environment in a flexible manner, at a resource agnostic manner in a sense. And I believe that to have that, you need a few main building blocks. So first, you need to have an abstraction that is flexible, yet abstract enough to define these jobs. Then, of course, you need to be able to run that abstraction on some kind of an execution system, like scheduling and allocating resources, and some way to manage these resources. So these are not particularly new, and you might ask yourself, hey, why is this hard, or why is this any different than the cloud? And my answer to you is, it is conceptually, an edge is nothing more than a very small data center. It's just a resource. But in reality, it's pushing everything to the extreme, and it's breaking a lot of the assumptions that we had when building these systems. I will talk about this in the next few slides and what I mean by that for each of those components. So if you think about the abstraction, in this new environment, you have a lot of different services. So like, for example, in the cloud, you have Azure Stream Analytics, you have Azure Functions, you have Azure ML, and these are each separate services grown organically and not completely in a unified manner. And they each have their own separate cost models, different APIs, and you want to now run them like as one big service, and actually be able to run that service on the edge itself. So you want to run centralized services now in a distributed manner. And so you want to have some way that you can have a single unified application from the point of view of the user. So they just write their application once, but they can use all of these capabilities, and that unified application can be deployed and then also monitored across the whole environment. If you think about the execution, or essentially the scheduling and allocation, now you have geo-distributed edges, but instead of just a handful of data centers, now you have millions and billions of locations. And also, these edges are limited in their resources. So they're not like this almost infinitely scalable cloud where you can just go and ask more VMs and more resources and scale everything up. But now you have a limited machine that actually doesn't have that good of a network. So it could be just a simple Comcast network to the cloud. And then it brings this whole big question of how do you make the scheduling? Like, which parts should be running on the edge? Which parts should be running on the cloud? If you have multiple jobs running, how do you allocate resources across them? And that is also along with all these constraints you had, like the latency constraints, the cost constraints, the policies that users might have in terms of where they want or do not want to run their applications, and so on. And then the last part is resource management, where now you have many, like for a typical enterprise scenario would have thousands of edges, and they're very faulty, so the edges themselves can fail, the link is not that reliable anymore, and it has actually many more causes of failures, as simple as somebody just plugging it out. And they're actually pretty heterogeneous as well. So an edge can be as small as a very small Raspberry Pi to a big multi-GPU server. So it is a very heterogeneous environment, and then it brings up this whole question of how can you manage all of these edges and the very diverse jobs running on them. So to sum this up, I think the main questions are how do you have a unified abstraction that can capture all of these diverse services? How can you execute in this big heterogeneous environment? And then how can you handle these faulty edges? But of course, these are not the only questions that need to be answered. There are many questions around security, like if you have multi-tenancy, how do you provide the isolation that you need? What about if you want to run a service like stream processing service on the edge? Or what about storage and what is the state on that edge? Like what if something fails? Is that data going to be there or is it going to get lost? And I think these are very interesting things to think of, but at the moment what I currently have been looking at is these main questions, and in particular I've looked at the first two questions and worked with Windows and Azure IoT for those two questions. I'll give a little bit of overview of what I currently have. So we've been working with them to first have a unified abstraction where you can define your job as a DAG of services and operations that you want to do, and simply provide where those services can be run. And then in the background, the system containerizes the services and runs them across the whole environment in a resource agnostic and a simple and minimal structure. Then we take that abstraction and actually deploy it across the whole environment. So we run parts on the edge, parts on the cloud, and provide end-to-end monitoring. This is a very hard problem because even right now, if you want to use different Azure services, you do not have one place that you can see all of your application services that are running. So you have different portals for each of them, but not a big view of all the system. And then the thing that I'm currently looking into is how can you optimize the scheduling. So I'm looking into minimizing costs, so monetary cost of running the service, while not sacrificing performance. And yeah.
So I understand the, I mean, each one of these seems like a big chunk, not easy to deal with. I think I can understand how you might be able to come up with an abstraction that allows you to specify, to containerize the work you want to do. And so it seems like containers are enough for you to give flexibility in where you run stuff. Is that fair to say that containerizing is maybe the key technique that helps you get flexibility?
It is to some good extent. So one thing is we didn't want to limit what the user can do. So essentially, if they are able to run a SQL query and run the service in like Azure Stream Analytics, we wanted to provide the same flexibility. So by abstraction, we're not changing what the users can code. So they code the exact same thing they would do if they were to run this cloud services. We're just abstracting the data flow. So in terms of how the service connect to each other. So whatever input you provide to write to the cloud, for example, you say, okay, this is my SQL query for my Azure Stream Analytics, and this is the DLL I want to have for my functions. And we don't limit that. The user can have the exact same thing they had. It's how we connect these and what are the missing pieces that are needed for you to run it across the whole environment.
So would Azure Stream Analytics like somehow live on the run on the edge?
Yes. So you need to have a containerized version of the Stream Analytics on the edge.
Oh, okay.
So at that we're working with the different services, like not just me, like the whole Azure IT team is working with the different services to provide that container.
Basically, like have Azure in a box in some sense.
Exactly.
On the edge, and I can.
It's a very horizontal project. It's not something that easy to do, but. The one problem is each service was grown organically, so nobody talked with anyone. They were just building these services and providing them. But now you want to unify them, so it's like the general problem. If you were to build them from scratch, you probably would have done a better thing, but that's not how things have happened. Sorry, yeah, go ahead.
So containerization, overhead associated with it. And I was wondering what level of overhead you're thinking about. So there's sort of function level, process level, VM level containerization.
These are process level containerization, but that's the general trade-off of isolation versus
Do you have a measure of the cost of the process level containerization?
So we're just using, actually not me, Azure IoT is using Docker.
Okay.
So they're just bringing up Docker containers. The thing that I'm doing is, so even if you have that environment that you can have containers, it's not as simple as just take the code and run it. You have to be able to unify it. And there are actually things like, hey, if I have, for example, some services cannot talk to each other. It's not like I can build any DAG I want. And like IoT Hub cannot talk directly to to DocDB. You have to add something like an Event Hub, which is a pub subsystem in the middle. So we're hiding those details as much as possible in a sense that the users can say, this is what I logically want to do. I just have a sensor and I'm just writing it to a database. I'm not doing anything fancy. You do all the details of actually gluing them together, setting up the routes, so how the data is actually flowing to the cloud and etc. So that's why I'm saying we're not changing the abstraction per se, we're changing the data flow and how things are connected. Did that answer your question? You asked about container overhead.
I'm still just wondering how much overhead is imposed compared to a more direct approach. If you can quantify that, that kind of tells you how much you're willing.
So I don't have numbers to tell you, but
in terms of the overhead, and if you could quantify that trade-off.
But the other option is to run it all in the cloud. So that actually takes more time than bringing up a container. So in terms of overhead, it is faster to bring. Like I worked a lot with Azure, and even if you just want to make a simple change, it takes a couple of minutes to put that change. But you can bring up a container, I think, within a second. So, but I agree that the container itself has overhead, memory overhead, and you could run them just as a process instead. Like the reason we containerize it is for portability, but you could run it as a process, which is lower overhead, but then you also have some isolation issues there. Yes?
What about the massive amount of data? Like, how do I deal with that?
Sorry, I didn't hear the first part.
Suppose I have a ton of data, and the work is operating on that data, and I use the cloud because that's the only place I can physically store it. Are you guys tackling that problem of how to bring just the right amount of data to the edge to be able to do the work, or are you not worrying about that?
So you cannot move everything to the edge. That is true. And we are moving the minimum amount so that we are reducing whatever we're doing in the cloud. For example, if you think about IoT sensors, your temperature is always the same value. And you probably are only interested when it changes. So you could write a simple filter or aggregation or some kind of a query that just filters out values that are above 60 and only sends those. Or look at the average temperature over a window of a few minutes. Or detects anomalies and only sends those. Or like, essentially you're reducing the amount of data that is being sent to the cloud so that you only send interesting events to the cloud. But there is a limit on how much you can move to the edge in terms of, it's not a cloud, it's not a multi-distributed system, but on the other hand, you also have multiple edges. So, yeah. Yes, sorry, go ahead.
In an IoT setting, what is the edge server for? So take a home automation type of IoT things where your fridge and your machine, your washing machine, everything is connected. Where is that server sitting?
So we were looking at the enterprise scenarios. That is what Microsoft is more interested. But like in a smart factory, you have a lot of sensors along with your manufacturing pipeline.
So this will be a few Linux boxes inside the factory.
Yeah, so the factory, like they purchase a few Linux boxes. In the home scenario, it's a little bit more fuzzy, I would say, because I mean, you could think, okay, I make my Xbox to be an edge. Or like, I don't know if I have Alexa or some kind of devices, but like Samsung is saying that you could make the fridges the edges as well because they have some smarts, but it's a little more in the gray area in the sense that is it worth doing that on a fridge or?
The proximity is, so the edge server assumption is that it's really proximal to where the sensor.
Yes. So that is one of the key things. It actually, like, I think it's actually pretty important that they're on the same network so you can talk over wireless, because if it's sending the data, it could send it to the cloud in many cases. But in this case, we're not sending it over the network outside of the whatever.
But then I have Sid's question. So if that's the hypothesis, so how do you deal with massive amount of data? Because I mean, then you're limited by the bandwidth that you have on this.
So
in a factory, take your factory example, right? If you are sending on a per millisecond or per second sensor data on each of the machines and the robots you have,
That's a lot of data. I agree, but what you could do is reduce that data right before you're sending it to the cloud. So
So is
some of
that
those
the
sensors,
developer's
there's nothing
job?
interesting happening, so you filter out and just send the ones that are
So would the
interesting.
developer have to actually understand the limitation of the edge in order to put it in his or her abstraction layer? Or
I
is
think-
that,
Mhm.
so is that complexity being shifted to the developer, or is the system actually handling that?
That is actually a very good question. So that complexity is shifted to the developer. So you're asking, does our system automatically filter out boring values or something like
Has
that?
to go somewhere, right?
So this is how we see it right now. So at this, what I have right now is this complexity is on the developer in a sense that even if you look at some of the pre-configured solutions that are out there, even in the cloud, they actually do the filtering, but they do it in the cloud because it becomes cheaper to send less data even to the following services. But I get your point that could we just completely abstract this out in a sense that the developer shouldn't think about the filtering. And something we thought about that is you could build some common modules like filtering or so one thing we actually do is compression and batching automatically. So when the data is being sent to the cloud, we do automatic batching and compression. But similarly, you can think about filtering, anomaly detection, and build these common modules, and then they can actually just say, hey, I want this feature enabled. And you could do that. But I'm not doing it at this moment. But that's a very interesting.
Seems like overall a top-level problem that you maybe won't be able to completely take away control from the developer, but you could provide things like modules or ways to make it a lot easier.
Yes.
To
So we do not actually want to take control away from the developer,
Yeah,
but
yeah.
I think it's important that you provide these as additional features. If they want to rely on us doing it, you could do it. Did I answer your question?
Yes,
Did you
thank
have a question? Okay. And yeah, we have integrated this whole system on top of the production Azure IoT and services, and we actually pitched it to I think the PMs there, and they're pretty interested, and we're moving forward with pushing some of this to their services. I would like to thank all the great people I had throughout these years, my advisors, Professor Gupta and Campbell, the great people at LinkedIn, and the awesome researchers at Microsoft Research. So throughout this talk, I talked about one of my work, which was a geo-distributed storage system and the future work. But I worked on a few other things, and I'm happy to discuss them later on with you in our one-on-one meetings. So I worked on stream processing, specifically how can you have stateful stream processing. So how can you have a lot of durable data along with your stream processing system, and what are the options and trade-offs there. I looked into container communications and how can you improve container communications considering the locations of the containers. I looked into auto-scaling stream processing in a sense that how can you automatically scale how much resources you assign to your jobs. I've looked into when should you go to the edge or not, just an overall analysis. And also I looked into how can you do I call schedule caching. So essentially you use the information in the scheduler that has the big picture of the job to make better caching and prefetching decisions. So that is my work, so I'm happy to take any questions if you have any.